Let's look at an example of population growth. Now, we're going to read this question carefully to really unpack what it's trying to say. So, in the first sentence, when we read it, it says, a bacteria culture grows with a constant growth rate. So, when I look at that term, constant growth rate, what that's really telling us is that's really telling us that we're in this situation where when you look at the relative growth rate, let's call it dp dt, relative to the population size, that's actually going to equal to a constant. Okay, so right away we know how to solve these types of problems from our previous video. We know that we're really going to be solving the differential equation that we just wrote. And we're going to understand that the solutions to this system look like this. It's going to be the population with respect to time, and that's going to be equal to some constant c times e to the kt. Okay, so once we know that we have a constant relative growth rate situation, we know that we have a differential equation that looks like this, and we know that the solutions to that differential equation will look like this. Let's read the next sentence together. The bacteria count was 400 after 2 hours and 25,600 after 6 hours. So I could take those two pieces of information, I can just translate it like this. They're basically telling me that P of 2 is equal to 400 and P of 6 is equal to 25,600. So when we read what part A is asking us to do, part A says, what is the relative growth rate? Express your answer as a percentage. So the relative growth rate, that's really going to be this K. So when I look at question A is really asking us, what is K equal to? And what I could do is I can use one of these 2 points along with this equation right here to solve for what K is. So maybe I'll use this second point right here. Now, when I look at this equation right here, and I'm trying to solve for K, I have a small issue. I know what the output value is going to be for a particular time, but I don't know what um, the initial population is. So what I'm going to do is I'm actually going to reinterpret this question. I am actually going to treat 2 hours as t equal to 0, and basically I'm going to have 2 hours be my new start time. This is my new start time. Okay, so when I do this, then my p of 0 is going to become 400, and my p of 4 is going to become 25,600. Okay, so I'm really redefining my original times, and I'm just going to shift everything by 2 hours. So when I view things in this way, then my equation becomes easier to write down. So I know that the output is going to be 25,600. I know that because I've shifted everything over by 2 hours, my initial amount is actually 400, and the K is what I'm looking for. And now I know that since the 2 hour mark, another 4 hours have elapsed, so that I'm going to put a T equal to 4 up here. So I hope this isn't too confusing. I simply redefined a new start time, and my new start time occurred at the 2 hour mark instead of at the 0-hour mark. And I redefined 2 hours to be the new t equal to 0. Okay, great. So now I'm just left with solving this equation. So I simply divide both sides by 400. I get 25,600 divided by 400. That's going to be equal to e to the kt, e to the 4k. Now I'm going to take natural log of both sides. When I take natural log of both sides, this gives me 4k is equal to natural log of 25,600 divided by 400. And to get my value of k, I simply divide both sides by 4. So I'm going to get k is equal to 1 over 4 times natural log 25,600 divided by 400, which is just 64. Okay, so this will be our value of k. Let me highlight that. All right, great. Let's take a look at the part B. So for part B, they're saying, what is the initial size of the culture? Okay, so when we look at part B, we need to remember that the general solution to our differential equation is going to be P of t equal to C e to the k. Now we just figured out what our k was. Our k was 1 over 4 natural log of 64 times t. And our question really is, what is c equal to? All right. So at this point, this c refers to not my new shifted starting time, but the original start time. So I am going to use the fact that originally P of 2 was equal to 400. So I'm just going to substitute both of those into our general solution. So we're going to get P of 2, which is 400, is equal to C, which is what I'm solving for, e to the 1 over 4 natural log of 64 times 2. Okay, great. So let's simplify this exponent right here off to the side real quick. Okay, so the first thing I want you to notice is that 2 times 1/4 is equal to 1/2. So that exponent becomes 1/2 natural log of 64. And now I can use the power law for the law of logarithms. That's going to be natural log of 64 to the 1/2 power. And we know that the square root of 64 is actually equal to 8. So this becomes natural log of 8. Okay, so what I just did was I just simplified this exponent right here. Okay, great. So now our equation is going to be 400 is equal to C times e to the natural log of 8. And we know that e and natural log are inverse functions of each other. So we have this cancellation property. And 8 is inside the domain of natural log. So really this equation now becomes 400 is equal to c times 8, which of course, when we divide both sides by 8, we end up with c is equal to 50. So that means that our initial population is 50. All right. All right, folks. I'm going to continue this example in the next video. Take care.